All right, everybody. I guess we'll start in a few minutes here. Just wait for a few more people to attend. But in the meantime, I'll do a quick little introduction to our two presenters. So on the left, you will see Rolfe. Maybe give a wave, Rolfe. And Rolfe is currently the president of Thoeni North America and is located in Vancouver, Canada. And we are a wholly owned subsidiary of Thoeni GmbH, which is headquartered in Austria, which is where Marco presently is located. And we are a leading global supplier of high solid plug flow and CSTRAD systems. Rolf's been involved in all aspects of the biogas industry in North America for about the past 15 years, and he's a past board member of the American Biogas Council. Fun fact is that Rolfe is planning to walk away from work for a month in October and hike the Camino del Santiago. So he'll have some pretty flat feet after that and some blisters, I'm sure.
Hobbit feet.
And Marco Grosze-Holz is a process engineer with over 30 years of experience in the research, design, and building of process facilities, focused on compost, biosolids, and digestion systems throughout Europe. He's currently the product manager at Thoeni GmbH in Austria. And a fun fact about Marco is that he's a fanatic mountain biker and has biked all over the world with plans to eventually participate in a multi-day race hosted here in my neck of the woods here in British Columbia, Canada. So we'll see if he ever gets here one day. So
yeah, would be great.
Yeah, exactly. So just to let everybody know, we're going to use the Q&A section of the presentation to ask any questions, which Rolfe and Marco will take at the end of the entire presentation, just so that we can continue with a smooth flow. And then we'll have 15 minutes at the end of the presentation to answer any of the questions that you've put into the Q&A. Throughout the presentation, we're going to also ask a couple of questions in the Q&A that we'll be curious to see what you guys' thoughts are before we actually reveal the answer in the slides. So over to you, Rolfe.
Okay, thanks, Carmen. Yeah, and I want to welcome everyone to our webinar on integrated anaerobic and aerobic treatment of mixed waste organics. But first, I want to address, I guess, the elephant in the room. Okay, there we go. Sorry. How do you pronounce our name? This is, ever since I started working with Thoeni about 10 years ago, a lot of quizzical looks at how do you pronounce that for most of our North American compatriots. Well, it really depends how if you're a European, you're familiar with the O and the two little dots above it, and you go Thoeni. An American might quite often say Tony, and, considering Tony Montana, Tony Soprano, and of course, Canadians, we give homage to our $2 coin, Thoeni. Personally, I go Thoeni, but whatever you call us, we're here to help you with your organics challenges. Thoeni has been in the environmental business for over 30 years now, and we're really known for our high solid anaerobic digestion systems. We have both a high solid wet system, which is called our TNV system, and our TTV, which is our high solid plug flow system. Both are characterized by a very robust agitation mixing system, which you need to manage those high solid, high impurity feedstocks that we see in a lot of urban and agricultural settings. Now, we've been very successful throughout the world with our systems, primarily in Europe at this stage. We have 93 different sites handling our TNV system, our high solid wet digestion, and 41 of our high solid plug flow. So we have a lot of experience with a wide variety of wastes throughout the world. We're proud to announce that we've started construction last July, actually in 2024, of our project using our high solid plug flow system for the city of Calgary. It was an expansion on their existing in-vessel compost facility. We should be completed around January 2026. Our partner, AIM Environmental, is the operator of that facility. The inputs for this system will be residential yard, garden, and food waste. which in Western Canada is quite a common mixture. They're co-collected in one bin, and that therefore necessitates the use of our system to be able to handle that kind of a mixture. It will be processing, once it's operational, 70,000 tons per annum of this yard garden, food waste, and residential mixture. For this facility, we've dimensioned 2 of our TTV 2450 digesters. The 2450 represents the cubic meters of digestion volume. So in this instance, we have 2 2450s, or 4,900 cubic meters of a digestion volume. The outputs of the system will be RNG and compost. And to the left, you can see some pictures. These are very recent. Our 135-foot shafts, 2 of them, just got delivered to Calgary last Friday. So we were happy to see those make it from Austria all the way to Calgary. And here you can see just some recent concrete pouring that we've been doing at the site as well. So very excited about this project, our first one. And once it's completed, I'm looking forward to touring people through that facility. Today, we're going to focus a little more on this project. It's a project that we're partnering with Zero Waste Energy, which is a subsidiary of Bulk Handling Systems. We're going to start construction next quarter, Q3 2025, and complete it in Q1 2027. This one will be processing OFMSW, or the organic fraction from MSW, also called MRF fines. When it's completed, it'll be processing around 65,000 tons per annum of that material. For this facility, we dimensioned 2 of our TTV 2250 digesters and 4 of our TGV IVD tunnels, or in-vessel drying tunnels. This one is unique in the sense that the outputs will be RNG. They're also going to be liquefying the CO2. And then the solid fraction after the digestion will be an ADC product, or alternative daily cover, for that system. Now, how do organics get into the MSW? It's pretty obvious. Really, over 70% of the North American population does not have curbside organic collection. So it goes where the rest of the garbage goes right now. Waste surveys show that the organics represent roughly 30 to 40% of that MSW stream. So it's a significant amount if there's no curbside organic collection. And what we're finding in other markets where they do have curbside organic collection, there's still about 20% of the total volume of that MSW is organic matter. Now, why does this matter? Well, if it's left in the black bag or in the MSW stream that goes to the landfill, there's significant fugitive methane emissions from the landfills as a result of these organics. And really, with or without landfill gas collection system, because these systems, their efficacy varies significantly depending on the design, the cover type, the operational practices, whether it's a closed landfill or active landfill. It's a significant issue. The other issue with organics in landfills is that organics take up space. And as you're quite familiar with, a lot of landfills, particularly near large municipal areas, their capacity is very strained and they have limited lifetime. So any material you can remove from that stream going to the landfill helps extend the life of those landfills significantly. And as we all know, permitting new landfills is a big issue and nobody wants it in their backyards. So I think at the end, there's a real need to reduce the mass and capture the methane from the OFMSW material prior to landfilling. Now, as I mentioned, Lane County, Oregon, this will be a great example of our integrated facility, where we have both a separation process up front, an anaerobic digestion process, followed by an aerobic treatment process. Now, in this case with Lane County, the county itself will be investing in the mixed waste MRF. That's the receiving area, as well as the separation processes internally, the grinding, the shredding, the separating out the recoverable, recyclable plastics and metals, and etc. But what's left over is this OFMSW feed, and that's the material that we will be handling going forward through the balance of the plant. OFMSW, as you can tell by the pictures on the right-hand side, it's not your average AD feedstock. In fact, this is a wet digester operator's nightmare. But that's exactly why we need, and we've used our Thoeni TTV system in this case that can handle that material. Just to characterize it, it's roughly 2 to 4 inch minus product. It's upwards of 45% total solids, lots of inerts, as you can see. It also happens to be where the majority of the organics in the black bag garbage are found. To handle this material, we've dimensioned, as I mentioned previously, 2 of our TTV 2250 digesters, high solid plug flow digesters, to handle that material. In this case, we used our steel digester version. And note the steel digester housings for these facilities will be manufactured in Eugene, Oregon by BHS. We did this for a couple of reasons. Back in the heydays of the IRA and the ITC credits, there was that extra 10% kicker that developers received if they used a certain percent of US steel components. So that worked very well in that case. But also, given the uncertainty now of the tariff situation, having a domestic manufactured significant, housing, steel housing, also will benefit us and allow us to manage a little better that tariff costing on our pricing. Now, how do you take that very challenging material and enter it into the digester? To do that, we have our patented mixer system, which consists of a couple augers that rotate in different directions in a pre-sequenced way. We take into this mixer about 2/3 fresh OFMSW, plus about 1/3 of the mass of inoculum or digestate from the back of the digester, and any other dilution liquid that we need to get that mixture down to around 32% total solid, which is our sweet spot for going into the digester. The mixer itself has about a 9-minute cycle. Once it's finished mixing all those 3, it drops into the piston cylinder and is piston pumped through a double-jacketed heating pipe. So we get that material almost up to thermophilic temperatures before even going in the digester, and that really helps with the whole process. Now, once it's in the digester, how do we prevent sinking layers and floating layers? How do we manage all those contaminants in that digester? And this is really where some of the benefits of our system are really play out. And I've got a little video here to explain it.
High impurity content is no problem for the Thoeni TTV digester. The substrate is fed into the digester by means of a piston pump. The TTV is ideal for the digestion of organic material with a high amount of impurity content. The impurities are transported safely along the TTV digester from feeding to extraction. The special design and configuration of the paddles along the shaft prevent sedimentation and floating. That way, impurities are continuously transported to the digester extraction and have no chance to build floating or sinking layers. This ensures constant maintenance-free operation of the digester, even when the input material contains high impurity content.
Great. So after we've had roughly, material's been in the digester for about 20 days for average retention time, the material is pumped out of the digester, extracted out of the digester to our dewatering systems, which are necessary. As you can see on the top here, the digestate comes out of the digester at roughly 26% total solids. We need to run that through a screw press to remove some of the liquids. So we end up, after the screw press, it's a specialized screw press. I believe it's a Belmer in this case. We have dewatered digestate, has a total solid of roughly 40%. The liquid fraction comes out at roughly 20% total suspended solids. Now, we do need some liquids, as I mentioned earlier, to dilute down the incoming material. But at 20% total solids, that liquid has too much solid and would create some challenges, operational challenges over time as it gets recycled through the system. So we run it through a pyrolysis centrifuge in this case, and it produces a liquid fraction of about 14 to 16% total solids, which is fine and adequate for our dilution purposes. The centrifuge produces the retentate, has roughly 35% total solids. That gets mixed with the dewatered digestate as well as structure material into an inline mixer to prepare it for the IBD. I'm going to pass it over to Marco now, and he'll take you from there.
Thank you, Rolf, for this anaerobic introduction. And I want to take you all into my world of aerobic treatment of organic solids. I will share my screen to take over the presentation. So you can see my screen now.
Do you want to put it in slide mode, maybe, so you can, or maybe it is. Okay. Okay.
Which screen? It should be the big screen now. Or you have the side screen as well.
Yeah, it looks good.
Okay, looks good. So about the aerobic treatment process, where we are in the whole process of AD, like Rolf has explained, this graph already, we are behind the TTV AD system, where we have the dewatering and the mixture of dewatered materials like retentate and digestate will be mixed with structure material and then filled into tunnel. We have automatic filling systems for that, and that's where the aerobic treatment happens. We do that with a fan, aeration of air across the surface of the tunnel floor to aerate all the material and process it further. How do the different materials look like? OFMSW, you have seen already before, like Rolf showed you. And then we have dewatered digestate. Unfortunately, I don't have any digestate dewatered from OFMSW because it doesn't exist in Europe. We have yard garden food waste instead of that. But it looks more or less the same, but what you miss here are the contaminants from OFMSW. Then you have the retentate. That's a sludge-like material containing a lot of heavy materials like sand and other minerals. And then we have structure material, and in fact, this mix we need to process in our tunnel system. And the structure is very important for us because these materials are quite dense, and as we have a process where we blow air through the material, we need some permeability of the materials. So that's why we need to add structure material and mix it thoroughly. How does the mixing concept look like? We have our dewatering, either the screw press or a centrifuge. This dewatered solids will come on a conveyor belt together with structure material, which we stuck in a bunker, and those together with the solid dewatered materials into a fluidized inline mixer. And we chose a fluidized bed mixer because that gives us the best permeability of the components we mix together. The output from the mixer goes on a conveyor, and then it can be discharged directly into the tunnels. So you don't need to handle it extra, or you drop it somewhere on a dropping point and take it with your wheel loader. But of course, you have extra handling on that. How does this mixer look like? It has a static drum with a shaft with paddles on it, and the paddles are orientated in a specific way. When you mix the material, you have one step mixing back, 2 steps mixing forwards. So this gives us a kind of back mixing, which makes a very homogeneous mix at the end. The example you see here, it's a mixer with 24 cubic meters per hour, and that has 1200 liters of a drum volume, but you can have bigger mixers like this, and they can go up to 100 cubic meters or even more, but we don't use them in the waste industry as we don't have that big capacity. For this small mixer, 24 cubic meters per hour, the footprint, the width and the length is about 5 meters long, 1.5 meters wide, or as you like in feet, 16.5 feet times 5 feet approximately. So it's a quite small unit. And the internals are highly wear resistant, as this machine has its origin in the mining industry. So they know how to keep up with a heavy wear, which is of course present in your OFMSW or other solid organic material. And as I said before, the mechanical generated fluidized bed mixing has proven to be the most suitable technology to improve CPP data. On the CPP data, I will come back later, but CPP stands for compaction, porosity, and permeability, which is important for us, important parameters for us to have a good material that can be aerated. And how does it look like in the mixer? We have a short video where we look on top of the shaft and where it mixes the material on quite a high velocity. And you see that the input materials, it were very sticky materials, digestate with retentate. And once you mix it, it's getting a loose mix that's easy to aerate, or better to aerate, I must say. So the in-vessel digestate processing, which is in fact a composting technology, is a biophysical process where aerability of the material is key for success. I mentioned the CPP data, compaction, porosity, permeability. These data need to be in specific measures. Otherwise, the material would be too dense, and if we cannot aerate it, the process will not run properly. If you process OFMSW, and then we call the tunnel system an IVD, in-vessel drying, where the focus is on heat production and ammonia hot stripping, because that's a requirement for ADC material, which is the end product from OFMSW. If you have yard, garden, and food waste, we call the tunnel system an in-vessel composting system, where the focus is on organic stabilization, volume reduction, and drying, and your end product is a high-class compost, which can go to agriculture. The system is capable to kill pathogens if possible. We can maintain temperatures up to 170 degrees Fahrenheit. We keep that for a longer time. European requirement says you need to do it at least 3 days and then maintain 130 degrees Fahrenheit after to kill pathogens. And that's all possible with the organic material which is inside your waste. So we don't need to use external heat, but we can to speed up the process. With every aerobic treatment process of organics, you have odor components that must be managed. So our exhaust air treatment consists of a scrubber to eliminate ammonia and also a biofilter to eliminate volatile organic compounds, which are both very odorous components. And with this closed system, this tunnel system, we have optimal conditions to prevent methane and nitrous oxygen or laughing gas emissions, which are both very strong greenhouse gases, which we want to prevent to emit in the environment. For instance, methane is 20 times more potent than carbon dioxide, and nitrous oxygen has a 265 CO2 equivalent. So that's a quite strong greenhouse gas. You don't want to emit them. To understand the process in more detail, I want to go a little bit into the theory of aerobic solid processing. So what is the definition of an aerobic organic processing system? It's a controlled thermophilic process where organics degrade by microbiological activity with the use of oxygen, which is coming from air that we blow through the system, producing some reaction products like carbon dioxide, water, ammonia, heat, and biomass. Having said this, and looking at the definition of the aerobic treatment process, would you think this is an aerobic or an anaerobic process? Question for you. You can answer in the chat if you like, and I will elaborate on that. If we have an AD system, most of you are probably familiar with this. You have 4 biological stages how organics are being broken down and transformed into biogas, which is methane and carbon dioxide. When we have the aerobic process, the air touches the anaerobic process where the volatile fatty acids will be consumed by microbiological activity and oxygen, and we don't produce biogas, of course, because it's not an anaerobic digestion, but an aerobic treatment, and we produce carbon dioxide, water, ammonia, heat, and biomass. So how does it look like on a particle size? When we have an organic particle, it's a solid particle containing biodegradable organics. That's material which is not broken down in the AD, because not all organics will be broken down in an AD system. Some only break down in aerobic treatment systems. And in this solid, we have the anaerobic hydrolysis from inside, because air cannot penetrate a solid inside. From this anaerobic hydrolysis, we have the production of volatile fatty acids, and because it's an acid, the pH goes down. Once we aerate this material, the volatile fatty acids will be consumed all the time when they are produced, and then the pH goes down to neutral, and we have the production of a carbon dioxide, ammonia, water, heat, and biomass. Biomass is the microbiological bacteria that multiply. When we focus on the heat that is being generated from 1 gram of organics, we need a certain amount of air, or actually oxygen, because the nitrogen doesn't do anything with it. And a significantly amount of heat will be produced, about 17 kilojoules of heat. And to have a feeling about how much energy that is, that's about half a cup of water, 70 degrees Celsius. I don't know, in Fahrenheit, it will be about 170 degrees Fahrenheit, I think. So really hot water, tea water, that's the amount that you generate in heat on just 1 gram of organics being decayed. So what happens if this heat is released? The material will heat up, and it will heat up the whole pile and the whole facility. And if we don't control the heat, then the temperature will raise up to 180 degrees Fahrenheit, and this temperature is too much for the bacteria to continue. So the process will kill itself. So we need to control the temperature. And how would we control the temperature? As we are using an air system, we blow through extra air through the system, typically 12 times more air than we need for just the oxygen supply. And then we can cool down the process, and this is exactly the way how we control the process, giving it more or less air to cool down or to heat up. How does it look like in a tunnel? I will take my pointer so I can show a little bit how it works. So we have this tunnel, which is a concrete construction with a big door that makes it a completely closed environment. There's a fan, optional a heat exchanger, and this fan recirculates air from the tunnel continuously. On this recirculation, we have a fresh air damper, so we can take fresh air from the outside, and introduce that in the system. And as it is a closed system, if you introduce something, something has to go out. So that's the exhaust. And how does it look like? We fill a tunnel with digestate mix, either by wheel loader or our automatic filling system. We close the tunnel with a big door, and we start the fan blowing air through the material. Once it does, it consumes oxygen, and the temperature will raise. So we'll see that the material heats up. Here we have an example of how it could look like. It's just an example, so not for all the systems it needs to be like that. So we heat up the material on a certain temperature, and then we keep that temperature. This is for pasteurization if you have yard, garden, food waste. And for an AVD, when you produce ADC material, we keep the temperature high to strip ammonia, because that's a requirement that the ADC material is free of nuisance odors. To control the temperature, we have this fresh air damper. It gives you more or less air to keep the temperature on a certain level. For yard, garden, food waste, we like to produce a high quality compost. That means that we have to break down a lot of organics without drying it before it's done. So we lower the temperature and we continue on a certain temperature, which makes the organics stabilize. And at the end, we need to cool down. And what happens then is that we close the recirculation, fan is still on, we take only fresh air from the outside, blow it through the material, and exhaust it to get rid of the heat. And then, in fact, the process is ready. We open the tunnel and excavate your compost or ADC material. So you see it's a batch system. So if you have a facility that wants to run continuously, we have different batches next to each other, so different tunnels next to each other to have a continuous process. If we are talking input materials, source segregated organics, we call the aerobic treatment process in-vessel composting. And the compost delivers, when you apply it on the land, delivers stabilized organic matter, but it's also a carbon sequestration of carbon in the soil. Compost is very important to improve your soil water retention capacity. It improves the soil porosity and the soil structure. And compost also takes care for nutrient buffering. Because of the amount of biomass which is in there, bacteria, it prevents soil and plant diseases, and at the end you have a higher crop yield. So TTV, the AD system, and TGV, the aerobic system, fit perfectly in the circular economy. Like shown here, you have your organic waste, you put it in the AD system, produce your energy in any kind. The digestate goes to the TGV aerobic treatment. We produce our compost, use it in agriculture. You have the benefits, grow the plants, and we eat the fruits. And that's a nice circle. If we are talking OFMSW, so you produce ADC material, we call the system in-vessel drying. And we don't have a closed circular environment. We have the input of organics in the AD system, put it in the TGV system, which is our aerobic treatment, and then you have your ADC material going to landfill. Focusing on ADC material, there are some requirements. The material must be leachate free, and there's a cone test to perform, and it must be free of nuisance odors. The leachate prevention we do by dewatering the digestate, mix it with structural material, and then dry it biologically or even thermal if you have a heat source available. And for maximum mass and volume reduction, we can dry up to 80% of dry matter content in your material, but of course that needs a long retention time, so also a bigger facility. And odor is reduced by hot stripping ammonia. So we raise the temperature in the system, and ammonia, as you can see in some graphs here, is easily emitted from the material at higher temperature. But also pH is an important role, but we cannot influence that. And also hydrogen sulfate, which is very odorous component, is oxidized, so we get rid of it. Now, coming back on the CPP, compaction, porosity, permeability, it's a test unit where we can test different mixtures under circumstances that simulate a pile in a tunnel. So once you have material piled up in a tunnel, material will be compressed because of the weight of the material itself, and that will influence the airability of the material. And it's important, like I have seen in the theory, that we need the air passed by all the solids to consume the volatile fatty acids, to get rid of odor, but also to stabilize the organics and to produce heat. And we have a test facility for that, where we can make our mixtures and determine how good or how bad a product, a mix, or just your digestate is aeratable. And having these experience and these numbers, we can make an efficient tunnel design and use tunnel capacity very efficiently. So what do we get from this CPP test facility? Different data about the compaction, bulk density, porosity, and the permeability. And at the end, we have a graph that simulates a tunnel. I have it enlarged here. What we see here is a tunnel which is filled up to 3 meters, as an example. And this is the pressure that a fan would have when it aerates at a certain capacity these materials. Material A is this yellow line. It's a digestate from a TTV facility from Germany, where I mixed 16% of woody material as structure in this. And you see with 16%, the pressure drop of the fan is quite low. So this material is easy to aerate. The air goes through quite easy. Sample number B is the same sample as A, but I added extra digestate in it. So the structure content is lower. And you see immediately that the pressure drop is significantly higher, although the structure content is only reduced from 16 to 12%, but it has a huge influence on the pressure drop. And that's why these CPP data are very important to us. Sample C is the same sample B with these 12% structures, and I mixed in retentate. And retentate is very dense, heavy, and sticky material. And once we mix it, we still could have a loose mix, but because of the CPP characteristics, you see that the pressure is very high in the system at a given fixed airspeed, that I call this one not aeratable. So we cannot, we cannot process this in our aerobic TGV system. About filling tunnels, I mentioned before, we have our automatic tunnel filling system, which is a conveyor that drops the material nice on a pile in the tunnel, which is already closed. So that has a big advantage on, for instance, wheel loader filling, where the tunnel is open and you go in with your wheel loader in and out. Having a closed system means that we don't have any odor emissions during filling the tunnel. So your AD system is closed. We have our dewatering, which is closed. We have our mixing, which is closed. We have our automatic filling conveyor, which is closed. We have a tunnel, which is closed. So here we have a fully closed system, no odor emissions. As from the first drop, we can aerate the material intensively. We don't have any issues with anaerobic circumstances, so methane emissions or hydrosulfate emissions, because we are in an aerobic environment immediately. because you have the automatic filling system, you have no extra bulk handling, so low OPEX. There's no spill from wheel loaders that drop material on the floor and drag it with the wheels all over your facility. And of course, no safety issues with heavy equipment driving all over. Because it's an automated system, you have the possibility to process your digestate overnight and also the weekend. And of course, it has a higher capex, which is a disadvantage of the system. The wheel loader tunnels are open system, like I said, and that gives you issues with odor and anaerobic issues. So methane, which is still in the digestate, can emit. You cannot extract that in a closed environment, so it will lead to odor issues, and also your sulfur H2S will give you some issues there. Of course, you have extra handling with the wheel loader, and you have your spill and safety issues having heavy equipment in the facility. But because the material is evenly filled, you have, in fact, best aeration conditions, because here we have the pile. And you can understand that in the middle, the resistance of the material is much higher than from the sides, but the counter effect is that we can aerate it from the first dropping, so we don't need to aerate the whole pile at once. And this one has the lowest OPEX, of course, because you don't have to invest in an automatic filling conveyor. And how does this automatic filling conveyor look like? It's type of screw conveyor with dropping gates, and the material is being filled here, transported to the end, and every dropping gate is filled one after another. Once the last is filled, we get a signal, and then all the gates open, it drops the material in the tunnel, they close again, and the process repeats. About the aeration, of course, we have an aerobic process, so air is very important. And for this aeration, we built air handling skids, and that gives a big advantage that you can construct your air handling unit in a workshop, so you have the clean conditions to make a nice skid built on that. The most critical components for processing are already built in, so temperature probes and pressure probes are already built in the skid. As it is a skid, you can FAT it before installation, and of course on the construction site it's easy to install this skid and connect it to your tunnels. Because the tunnel system is modular, we have a modular system with this skid as well. And also on the skids, we can mount the cable ducts and piping for your heat exchanger, which is in this box. We can pre-mount it, so your installation on site is very limited. Where do we position these skids? We can either position them on top of the tunnel or on the back side of the tunnel. It's very much depending on customer requirements, but also on the layout of the facility. And what we see here in this picture, that this fan has its exhaust on the top. But what we do is that we make the exhaust of the fan on the bottom, so all condensate which occurs or will form here in the ductwork will go together with the airflow out of the fan and go to the spigot pipes. We have a spigot pipe aeration system, and that has a condensate trap at the end, so we don't need any extra condensate collection piping from our air handling units. I very much get a question about how do you control or how do you check your air distribution in the spigot pipes, because the spigot pipe has many nozzles, and of course on the left side of the tunnel, right side of the tunnel, front or back, there could be a difference in air distribution, which we don't want. So the spigot system is designed in a way that we have an evenly air distribution. And I can show how even the air distribution is using ping pong balls. You have a little video here. You see the ping pong balls floating on the air stream coming from the nozzles. And once the ping pong balls have more or less the same height, we know that the air speed or the air capacity from each nozzle is more or less the same. And this is a test facility where we test our spigot pipes, and we found out by measurement, pressure and air velocity measurement, that the deviation in our air distribution is less than 10%, no matter where you measure. So we are always within 10% difference of air distribution. So, Rolf, I think I hand over to you for the results.
Okay.
For the wrap up.
Yeah, thanks. Thanks, Marco. I think we'll all agree aerobic processes are a lot more complicated than anaerobic processes, but I appreciate you going through all the details on that, Marco. So what have we seen, I guess, today as we're wrapping up our webinar here? We've seen the anaerobic digestion of mixed waste organics via the Thoeni TTV high solid plug flow system, and this allows the production capture of the methane and the CO2 from that organic matter, as well as weight reduction. And we've also seen the aerobic treatment of the resulting digestate via Thoeni's TGV system. And that, click the next one.
Sorry.
Depending, as Marco mentioned, depending on the feedstock, if it's yard, garden, and food waste, we can produce a Class A compost using our system. And if it's organic fraction from MSW, we produce the ADC that meets the cone test as well as the odor tests. And so what we wanted to show in the webinar was that you can get both an anaerobic and aerobic integrated solution from one supplier, and that's Thoeni. And maybe go to the last slide, Marco. And we just wanted to thank everybody for taking your time. I know on the East Coast it's lunchtime, so I guess you can go and grab your lunch now. Here's our contact information. If you have any questions, would like to reach out to us individually, please feel free. We will be sending out an email with a link to download the presentation in a couple of days, so you'll have that as well.
For anybody who asked questions, Rolf, if you just go to the Q&A area there, there are quite a few questions that were asked. So,
yeah, okay, let's go. Let's see. Okay, how does the system deal with macro and microplastics? From an anaerobic perspective, again, we treat the material as it comes into the digester. We're able to manage the macroplastics, plastics, or any other contaminants don't impact operationally our anaerobic digestion process. The microplastics, yeah, unfortunately, there's really nothing we can do to remove those, or if they're in the incoming material, they're in the outgoing material as well. So. There's a few questions here from Ed Weinberg. If the premixture is compostable, how much bigger would the facility footprint be compared to using the mixer with aerobic treatment? Okay. I guess I would have some follow-up questions, Ed, and I see you have a few other questions here. If you send me your email address, we can maybe connect and we can go through these in a little more detail. Certainly that one, I'd have to, a few questions I have on that. What is the average CH4, CH2, CO2 ratio with thermophilic biogas? Probably around 57% methane to, 33% or 43% CO2 is sort of an average, I would say. I don't think can be a little higher methane content with thermophilic, but that's probably what we're averaging.
And it's a little bit depending on your feedstock. So it depends if you have a lot of fats or carbohydrates or proteins that makes the methane content.
Correct. Yeah, exactly. Mackenzie Bernard, what is the CapEx and 10-year OpEx? We are just a sub-supplier to Zero Waste Energy. I can, if you send me your contact info, I can refer you over to our contacts at Zero Waste Energy, and I'm sure they can have a discussion with you regarding the pricing of that. Is the scrubber sump water ammonium sulfate usable as liquid fertilizer? I think the answer is yes, but Marco?
Yes. The ammonium sulfate from the scrubber for sure is usable as a nitrogen fertilizer. And I know from some countries, I don't know about the US, but I know from Australia, for instance, that it has a pretty high value, 200 Australian dollar per tons. It makes a perfect nitrogen fertilizer. So it can substitute chemical fertilizer in this. And very easy to apply. And it has about 5% of total nitrogen, meaning 25% of ammonium sulfate about.
Okay, that's all the questions I have here. Well, if that's it, then I'd again like to thank everybody.
There's still some more questions. So Ed has a couple more. What is the total CO2 emissions, anaerobic and aerobic, per metric ton input of waste, CO2 MT/MT waste? And how does that compare to the system total CO2 equivalent for MT/MT waste in?
Yeah, funny, I don't see this. Again, I think to answer those questions, I think I'll reach out to Ed individually and go through those. I mean, you've got a lot of good questions here. So is there another one from Ed? I can't find all of them. I can't see them right now on my screen.
Ed's, he supplied his email address here, so we'll send you.
Okay.
Jessica,
I want to say something. I want to say something about CO2 emissions. What we need to take into account is that when we have CO2 emissions from food waste or OFMSW, that's CO2 from a short cycle carbon. So that doesn't contribute in the CO2 balance of greenhouse gas. It's like you breathing CO2. It doesn't count in the carbon in the greenhouse gas emission. So it's short cycle carbon. So yeah, of course, all the organics, all the carbon that's being broken down will produce CO2, but it's only a matter of environmental impact if that's a long cycle carbon like oil, gas, and other fossil fuels.
Yeah, and as we talked about, as I mentioned, for Lane County, Zero Waste Energy, they've designed a CO2 capture and liquefaction system. And they'll actually be capturing that CO2 and selling that to a local welding supply company. So it still gets emitted one way or another, but as Marco said, it's biogenic CO2, so less of an impact.
But liquefying CO2 from a short cycle means that you're carbon negative, because you take this short cycle carbon out of the process, you use it somewhere else. So that means that long cycle carbon is avoided. So net you are carbon negative.
Yeah, exactly.
And that's the reason why we liquefy CO2 in some projects.
Yeah.
And Jessica asked, what kind of mechanical performance guarantees does Thoeni provide in terms of throughput, uptime, and maintenance?
As far as mechanical guarantees, uptime, I think we have 99% uptime guarantees. Throughput, again, very dependent on the type of material. To do that, we need to understand the feedstock inputs, and then we produce our mass balances. And then if we eventually get to contract, those mass balances form part of the agreement. And as long as the feedstock is within a certain range of parameters of total solids and a few other parameters, we're able to guarantee certain throughputs through the mixing system and through the pumps, etc. So.
All right. And Dr. Vanita Prasad Rebbe has asked, how much biogas recovery per ton of waste? So again, I guess that depends on the feedstock that's being used, correct?
Yes, yes. You know, it varies significantly, obviously, depending on the composition of the tonnage. You know, we go anywhere from, you know, let's say just yard garden material, maybe 60, 70 cubic meters per ton up to.
No. It's much more. From Europe, we have from yard garden food waste between 100 and 130 cubic meters of biogas per ton. And if we have more like OFMSW, because we have OFMSW digesters, but not aerobic treatment systems, I have seen facilities having 160 to 180 cubic meters per ton input.
Yeah, I was just giving a range, the low end being just the yard and garden, the high end being the SSO
From
and such.
So he's just asked from MSW is basically what he's asking.
Okay.
Yeah. And then we had one last question over in the chat. And have you tried using 90% oxygen rather than air? I'm assuming that was at 9:36. So that would have been in Marco in your portion of the presentation.
Yeah.
When you were discussing.
For sure, it would work, but if you have a high concentration of air or oxygen, that has a significantly capex. So we haven't tried it. I think it doesn't make a how you say a worth process. So it will cost you too much money, and the process won't speed up because the microbiological activity is just limited. I mean, these bacteria cannot consume more food than is being broken down, and the oxygen is needed, but it doesn't speed up the process. It's only when you have lack of oxygen, your process will stop, but more oxygen is not a quicker process.
And one last one from Ed, is your CPP material testing unit simply a residential scale cement mixer?
No, it's not. It's not. There was a residential cement mixer in one of the pictures, and I used that to pre-mix my mixtures before I put in the CPP. The CPP is a pressure vessel where we compact, where we compress the material, and then under repeatable circumstances, we aerate the compressed material, and then we measure compaction and porosity and permeability.
Perfect. That's the last of the questions.
Okay.
So.
Great.
Well, again, everyone, thank you very much for spending this hour with us. I hope you found it productive and useful. Again, please reach out to us if you have any questions and want to follow up. I'll reach out to a few individuals that did supply their email, and until next time. And if you have any challenges with your organics, please reach out to Thoeni. Thanks a lot, no matter how you pronounce it.
Exactly.
Thank you, everybody.
Okay.
Thank you,
Bye-bye
everybody.
from Europe.
Thank you.
Bye.